So good afternoon. So today we are going to continue creating a couple of other crystal structures from different space groups. There are some nuances that one might have to keep track of when you are constructing these crystal structures. So I'm first going to demonstrate what will happen if you have a monoclinic space group. So the crystal that we are going to construct is this one, CaMgSi2O6, okay, and it is told here that this particular crystal belongs to the C1/2/6 space group, or it can also be written as C2/C space group, which means that there is a C glide, there is a twofold rotation, and there is also some centering that is actually associated with this crystal. C centering is associated with this crystal, okay, and you have been given the A, B, and C lattice constants for this crystal, and the Wyckoff positions for all the atoms, calcium, magnesium, silicon, and oxygen, are given in this table right here. Okay, so there is calcium belongs to 4e, Mg belongs to 4e, and then there is a silicon atom which belongs to 8f, and there are also 3 oxygen atoms which belongs to 8f. So some of them are special positions, as you can see. There is a 0 here, while the others probably are general positions that are given to us. So we have to refer back to our crystallographic table in order to generate the entire crystal, right? We have to know what are the other points that are existing within the unit cell. Before we do that, it's important for you to for us to understand how the lattice vectors are actually specified for the monoclinic unit cell. So, so this particular point came up last class also. So why is it so important to actually keep track of these lattice vectors? So whenever when we are talking about the monoclinic unit cell, it is important for us to know how these lattice vectors are actually pointed with respect to our x, y, z axis. So this is our x, y, z axis, forming a right-handed system. And if you refer to the international tables of crystallography, this particular space group would have been specified in the following manner. You would see a A pointing to the right, and you would see a C pointing that way, okay, and the beta that is given to you is basically the included angle that is existing between A and C, okay. Now, how do you give the lattice vectors for this particular system? You should understand that the x fractional coordinate is associated with A, the y fractional coordinate is associated with B, right, and the z fractional coordinate is associated with the C direction, right, C direction. So we have to be careful in the manner we specify the lattice vectors for this. So it is obvious that the A lattice vector, if you try to write it in terms of our Cartesian coordinate system, is nothing but A 0 0, okay. The B lattice vector and the C lattice vector need to be specified, okay. So if our A is pointing in this direction and our C is pointing in this direction, right, then our so in what plane does the C vector lie? It lies in the xz plane, right, it lies in the xz plane. So consequently your C vector will have what as the components here? It will have C, this is beta, right. So what would it be? Can you please help me out here? What would the x component of the C vector be? This would be the C vector, right, because you are looking at it from the top. So this is what we want our B to be.
So the position of C vector is in the xz plane or is it
The position of C vector is in the xz plane. Xz plane, right? So that is what I am viewing it that way. You can actually associate any way you want, as long as you are careful about doing it. You will not have a problem. But being careful about is kind of important. It's not too obvious, as you will see. It's because until now, whenever we gave the C vector, we just did this, right? It was the last or the z component which had a non-zero value in the lattice vectors. But in this case, the projection is given on the B as viewed from the B axis. Okay, so if you call this as B and this as x, this as A, then C has to lie in the xz plane with an included angle of beta in between them. So what would be the x component of the C? Cos beta, maybe? Huh? Then this would have any y component? No. Y component. And what would be the z component? Okay. Now what about the B vector? The B vector is 0 B Z. Okay. So let us first go to our MATLAB script and do that. So we had 0 B 0, then I had C cos d beta 0 and C star sin d beta. Okay. So now we have defined our lattice vectors that we want to use for constructing our crystal system. The next task is to basically look at the Wyckoff positions and then define the various other atoms that are present within the unit cell. So once again we have to refer back to our crystallographic space group Wyckoff position. We will choose the Wyckoff position from this. We choose the space group first. The space group is C2 over C, right? So that belongs to the monoclinic structure. I have C2 over C right here. So it's 15. And these are the Wyckoff positions that I have. So the first thing is that calcium is present in position 4e. So it's 0 y quarter and 0 minus y 3 by 4, right? So these are the various. Is there something wrong here? 0 y quarter and 0 minus y 3 by 4. 0 some value of y quarter, and the other values can actually be defined in the corresponding function which grabs the basis, okay, where you would have defined the basis for each and every Wyckoff position. So this function basis underscore sim 4e is defined here, where all the other symmetry equivalent points have been defined, just like how we did for the other cases. Okay. Similar, or you can actually give CA2, since it only contains 2 points, you don't necessarily have to write a separate function. Like for example, 4e contains only, how many points does 4a contain? It contains 1, 2, 3 and 4 points, right? If you don't want to define the 4 points, you can simply give all the 4 points as a concatenated array for CA1, right? It's the same thing. But we will do it here slightly differently. We will give the first value and then the subsequent values will be defined in the basis underscore sim 4e function. Okay. Now mg1, where is mg1? So mg1 is now also in a 4e position, and therefore we can use the same basis function. We can use the same basis function because as far as 4e is concerned, the set of equivalent points will essentially be generated the same way. The only thing that is different is the value of the coordinates that you are giving it is different, but it is still a position, it's still a 4e position. Wyckoff position is still 4e. Yeah, this there is probably a mistake here. The mg1 if it is going to be present in a 4e position, then I should have this also as 0.25. So this is probably 0.25. So let's change that. Okay, if it is a 4e position, no, I might have made a mistake. Okay, we can check that quickly. So okay, maybe not. So let us have this as a 4e position and continue to have it as 0.25. The next silicon atom is actually in a 8f position. So these are the general coordinates, and all the other oxygen atoms are also in the 8f position. So consequently, I need to write only 8f function, right? And that function is right here with all the things defined according to as required by these things. So you see here in this table, Wyckoff positions of group C2C number 15, the unique axis is B. So they have made it important. They've told you that the unique axis is B, or the corresponding y coordinates that are existing here are going to be associated with that. Okay, so if you're not careful about this, then you will switch the definitions of the B and the C vectors, and you will not be getting the right crystal structure. And this can mean a lot of things, because the distances are changed now between the atoms, and when you give this to a molecular dynamics simulation, it can not converge to the right energy value because you are giving it a different crystal structure. So keeping track of how the origin and how the lattice vectors are actually defined is extremely important. So now, Smarak, is that aspect clear? You asked this question yesterday, last class. Why this? You asked why this is important to. How does it matter whether we drew something like this? So usually this would be A and this would be B. So how does it matter whether this is A, this is B, or this is B and it would be like this, right? B and A. And how would it matter if we wrote it this way? So in this case, it doesn't matter. Are you following? So yesterday we wrote something like this, right? I told you that in the international tables of crystallography, I want a larger eraser here. In the international tables of crystallography, you would find something like this. You would find this to be A, this to be B, maybe for the tetragonal space group, or maybe for the orthorhombic space group. And I also pointed out this could also be written this way. It's the same thing. You're just performing a rotation and all your Cartesian coordinates remain exactly the same, and there's nothing much change. In fact, you could define A if you were using this sort of a representation. We could define our A vector, or first lattice vector, to be the A vector could be 0 minus A 0. This one could be B 0 0, and it would still, our code would still work. It's not necessary that you do A 0 0 0 B 0 0 0 C. Okay. In monoclinic systems, the fact that they have mentioned that we are looking at a unique B axis, which essentially means the B axis is what is pointing outside the board, and the oblique plane is the AC plane, not the AB plane. And this is important, right? You couldn't treat the C as a B, because then it would get mapped to the wrong basis fractional coordinates, right? So for this reason, it is important for us to keep track of how these lattice vectors are actually defined in the international tables of crystallography. So once we do this and define all our basis atoms, I'm going to save it, and I have defined everything here, and I run this code. This is what I end up with. This is the crystal structure of my CaMg2. I would like to view it in a slightly different way, but I need to try something here. Nah, it's wrong. This is right. So this is your crystal structure for CaMg2SiO6. Okay.
Sir, which color corresponds to
Which?
which color blue is what?
Okay, so which color corresponds to which? So the if it's 1, then it's Ca1, 2 is Mg1, 3 is silicon, and 4 is oxygen. So we go back to our main website, the main program. So 100 is red. Red is probably the first one, Ca, right? Yeah, 1 is Ca, and red is Ca, then red, green, blue. This one is the other one, which is magnesium. The third one is the silicon, and then the remaining ones are oxygen. 4 is oxygen, which is the not the red, not the blue, and I don't know these two colors. If you put one here, I don't know what color it turns out to, but it is, you can find it out easily. This one is definitely the calcium. What is that? Yes? Oh, definition of symmetry 4E. Something wrong there? Multiplicity is 2, huh? Multiplicity is? No, 4E, 4, no? You have to add, see, in that, it's a centered lattice, right? So the multiplicity is, you have to add half to the 0 and the y coordinates when you are trying to define this. So this one, adding 0 doesn't change it. Then if you add half to the 0 and the x and the y coordinates, will give you additional 2 points, and therefore the multiplicity is 4. Correct, that's right. The side symmetry is a two-fold rotation. It is lying on a point which has a twofold rotation at this point. Is that clear? This is how you generate for the monoclinic structure.
Calcium and magnesium both have 4e equal position.
Correct.
So does that mean say the number of atoms in unit cell should be same for calcium and magnesium?
None. Yes, if calcium and magnesium are both present in position 4e, then the multiplicity is 4. So there will be 4 calcium atoms and 4 magnesium atoms, 8 silicon atoms, and there will be 24 oxygen atoms. Right? Okay. Are there any questions with this monoclinic lattice construction? Okay. The next one is slightly more, has more number of things to keep track of, which is basically the P4 space group. So tetragonal structure. In tetragonal structure, once again, it is viewed through the C. It is viewed from the C axis. So this is B and this is A. So you will be viewing a square. So the the axis which has a maximum symmetry is basically taken as the C axis. Okay, so you have A and B given to you, which are both equal, and C is 1.6714 nanometers, given P41 space group, and these are the various positions of CS and P, and all of them are in position 4A. Okay, so let us take a look at this particular space group. What did I say was the space group was 4 P41. These are the various atoms. There is one general position, that's it. There is no other, there are no special positions in this entire thing. So XYZ and all these things can be easily generated. So once again we go back to our original code. What do we have to change? We have to change a very few things actually. We just have to change the corresponding lattice vectors. I will comment out the lines that we had for calcium magnesium silicate, and uncomment these lines, and of course I have to define the appropriate lattice vectors, so which I have already defined here. And then finally I just have to change the corresponding function that I will call CS3P7. And that's the crystal structure for CS3P7, the one unit cell, just one unit cell, which with of course the some of the boundary atoms are turning up here, and the reason for that is that we have said you print 1.1 here. If I change this to just 1, as I mentioned in the last class, you would not see those atoms, right? This is how the axis view. This is the XY axis, so this is going to be the A, and this one is going to be B. Okay, the Y axis is B here. This is actually a square. This is actually a square, and you are looking at it from the top. The C axis is pointing outside the board. Okay. The rest of it is all pretty straightforward. It's all quite similar. For this, for this particular space group, it is advantageous because there is only one function that you need to write. There is only one Wyckoff position in which both the cesium as well as the phosphorus atoms are actually located. Okay.
So in that website, there is the option XYZ. If you put manually, you can get all the.
So one of the question is, in this website there is XYZ. So can we put some number here and get all the optional atoms? Let us try. This is what it gives. So it gives you that the Wyckoff position is 4A. Okay, and it doesn't give you it gives you the entire list like what you are expecting. But let us see this one. Basically, if you give the fractional coordinates, it is going to tell you what is the Wyckoff position. For example, I am going to say 0, then I am going to say 0.334, and then I am going to say here 0.25. So so it says that it is 2C. It says that the position is 2C. So I am able to give the position, and it is telling me what is the Wyckoff position in which that particular point is located in. Okay. Usually we don't have that sort of a problem. We only have the other problem. We only are given the Wyckoff positions and we have to generate the crystal structure. Now let me do one last example where we have I want to show you the structure of selenium, which is Trigon. Okay, so this one we'll take a look at it first from the website. Selenium has a trigonal structure, okay, and its space group is P3 suffix 1 to 1. So it's so this is the space group. So we use, what do we use for such trigonal systems? What is the unit cell that we use? We use the hexagonal unit cell with 120 degrees included angle between A and B, okay, and C is pointing upwards. So this would be the lattice vector. Something like this would be the lattice vectors, and C is pointing outwards. Oh, sorry, this is B and C points outwards. This is B, okay, B, it's B, not C. So these are the lattice vectors: A00, 0, B cos D 120, B sin D 120, 0, and 0, 0, C is basically my C vector, okay, and I am going to comment them and look for my selenium thing right here. These are the lattice constant. By looking at the lattice constant, you can know this is A, this is B, and this has to be C. It's pointing outwards, okay, and I have to change my this one to SE. That's it, okay. So let us take a look at where these atoms are actually located. Symmetry position is 3A, P3121 from the materials project website, okay, and we can also look at our P3112 or 21, what, this one, right? So this is the general, this is the position. So they are at positions 3A, okay. So there will be only 3 atoms present inside the unit cell, and as you can see, when we generated it, there are just exactly 3 atoms that is associated with the unit cell. And you can also check if this is correct by going to your materials project and look at this. So now if you see, there is 1, 2 and 3, all the other atoms are located outside of this unit cell. So so you can make other you can like I showed you the other day, you can click edit crystal and then remove the other atoms that are present outside the unit cell, and convince yourself that whatever you have created is in fact right. So this is a very good way of checking your codes. So one of the first things that you will be doing whenever you are running molecular dynamics simulations is to create the crystal structure, okay. Not always are crystal structures, BCC or FCC, for which the you can get away with writing some simple codes. When they are monoclinic and tetragonal, you have to be careful, and when each unit cell contains a large number of atoms, then it becomes extremely careful for you, it becomes extremely important for you to generate these structures correctly, right, and also check them, right. You can create a unit cell on your MATLAB, check them and use that to generate your crystal structures for the molecular simulation package that you are going to be using, okay. So with that, actually I have completed the first module of this course, which involves creation of crystal structures, interpreting space groups, point groups, understanding them, and how you use a Hermann-Morgen symbol and the corresponding Wyckoff positions for every space group to generate any crystal that is given to you, right. So from the next class onwards, we will start with the next module, which will involve some introduction to statistical mechanics. So statistical mechanics is a vast subject in itself, okay. It is not something that we can actually cover in 1/3 of the course, but it so happens that the molecular dynamics, the reason why molecular dynamics framework works, why it is giving you useful results, is because of the framework that is established in statistical mechanics, okay. So it is a good idea to actually look at statistical mechanics first to see what that framework basically tells us, and then come back to molecular dynamics simulations, and you will be able to better appreciate the kind of results that it is producing, and also interpret these results whenever you are doing your research work. Okay.